Welcome to my online course in linear algebra for undergraduate mathematics. In this lecture, we will discuss some theorems on isomorphism. First theorem is to finite dimensional vector space are isomorphic if and only if they are of same dimension. First, we will consider two vector space of same dimension. Then we will show that they are isomorphic to each other. For that, we consider U and V be two finite dimensional vector space over the field F. First, let time of U and time of V are n. If time of U and time of V is n, then basis of U and V will contain n elements. So we consider P1 equal to U1, U2 dot UN be basis of U and P2 equal to P1, P2 dot Bn be a basis of P. If U belongs to U, then there exists unique scalar alpha 1, alpha 2 dot alpha n such that U can be expressed as the linear combinations of this scalar and the vectors of B1. As given by this U equal to alpha 1 U1 plus dot alpha n UN. And correspondingly, alpha 1 linear combination of this scalar and this vector belongs to V. There exists unique linear combination of this scalar and this vector in the vector space V. Okay, since B2 is a basis of P, so this is a unique element of P. Let us define a mapping f from U to V by f of U is equal to f of linear combination of the vectors U1, U2 dot UN. In place of U, I am writing this linear combination alpha 1 U1 plus alpha 2 U2 dot alpha n UN, which is equal to alpha 1 P1 plus dot alpha n Bn. We shall show that f is an isomorphism. First, we are going to show that f is linear transformation. For that, we will consider two elements x equal to alpha 1 u1 plus dot alpha n un and y equal to beta 1 u1 plus dot beta n un belongs to u, and alpha beta be any scalars in the field F. Now alpha x plus beta y is equal to alpha this element plus beta this element. Bring the alpha inside the bracket and write the coefficient of u1, u2, un. I will get this one. Alpha 1 plus beta 1 u1 plus dot alpha n plus beta n un. Take the f image in both the side. F of alpha x plus beta y, f of this element. Then use the definition of this mapping. I will get this value. Alpha 1 plus beta 1 b1 plus dot alpha n plus beta and bn. Then writing alphas with alpha and beta with beta, I will get this step. Then take alpha common, I will get this alpha into alpha 1 b1 plus dot alpha n bn plus beta 1 b1 plus dot beta n bn. And this is equal to alpha x plus beta y. This is from the definition of the mapping we have defined here. Next, we will show that f is 1, 1. Use the definition of 1, 1, that is f of x is equal to f of y implies x is equal to y. So, let f of x is equal to f of y, then put the value of x, that is f of alpha 1 u1 plus dot alpha n un is equal to f of beta 1 u1 plus dot beta n un. Again, using the definition of mapping, this is alpha 1 b1 plus dot alpha n bn, and it is equal to beta 1 b1 plus dot beta n bn. The next step, bring this to left hand side. Bring the right hand side term to left hand side, and rearrange. I will get alpha 1 minus beta 1 b1 plus dot alpha n plus minus beta 1 into bn. Since b1 b2 dot bn are the element in the basis b2 for the vector space B, That means this b1, b2, dot bn are linearly independent vectors. So this alpha 1 minus beta 1 scalar is 0. All these scalars are 0. If these scalars are 0, then we will get alpha 1 is equal to beta 1 and up to alpha n is equal to beta n. Therefore, alpha 1 u1 plus alpha 2 u2 plus dot alpha n un is equal to beta 1 u1 plus beta 2 u2 plus dot beta n un. That this implies x is equal to 1. Hence, f is our 1, 1. Next, we will show that f is onto. For that, consider an element in V. Let V belongs to V. There exists scalar alpha 1, alpha 2, dot alpha n. Since B2 is a basis for P, V can uniquely express as the linear combination of this scalar with the vectors of B2. That is, B is equal to alpha 1 B1 plus alpha 2 B2 plus dot alpha n Bn. This B2 is this one, B2. Okay. Then linear combination of this scalar with the vectors of B1, B1. This linear combination of the scalars and the vectors of B1 will be new such that this U can be uniquely expressed as the linear combination of the scalar and the vectors of B1, and this linear combination belongs to U such that f of U is equal to f of alpha 1 u1 plus dot alpha n un, and it is equal to alpha 1 b1 plus dot alpha n bn, and it is equal to p. Therefore, f is my onto. Since f is linear transformation, f is 1, 1, f is onto. Therefore, f is my isomorphism. Hence, f is isomorphism of u onto b. Conversely, f u and v are two isomorphic finite dimensional vector space. We shall have to show dim of u is equal to dim of v. Let dim of u is equal to n and s equal to u1, u2 be the basis of u. To show dim of v is equal to n, since f is isomorphism, f will carry these vectors to v. That means f of s will be f of u1, f of u2, f of un. If I name this set by s1, s1 equal to f of u1, f of u2, f of un. To show dim of v is equal to n, we have to show that set will be the basis of b. Okay, to show this set is a basis of P, we need to show that S1 is linearly independent and linear span of S1 is equal to B. So let alpha 1, alpha 2, alpha n be scalar such that linear combinations of this vector with the scalar is equal to 0. Here 0 represents 0 vector of P. Here I am not writing 0 dex. Instead of 0 dex, I am writing the 0. But you must know which 0 denote which vector space 0. That is 0 belongs to U or 0 belongs to P. You must know this one. Here these are the element of P. So this 0 is the 0 vector of P. So alpha 1 f of u1 up to alpha n f of u1 is equal to 0. Again, using the properties of linear transformation, I will get f of alpha 1 u1 plus alpha n un is equal to 0 since f is linear transformation. Again, by using the properties of linear transformation, in place of 0, as 0 is the 0 vector of P, I can write f of 0. Since f is my 1, 1, so this element is equal to this 0. That is alpha 1 u1 plus alpha n un is equal to 0. u1, u2, un are the element in the basis b1 of the vector space u. That means these are linearly independent set. So this scalar are my 0. Therefore, S1 is 0. Since linear combination of scalar and the vector are 0, we have got scalars are 0. Therefore, my set S1 is linearly independent. Next, we shall show that linear span of S1 is equal to P. Since f is on 2, let v belongs to v, there exists unique u belongs to u such that f of u is equal to my p. As u belongs to u, so there exists unique scalar alpha 1, alpha 2, dot 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 alpha n, such that linear combination of this scalar with the vectors in the basis for u is given by u equal to alpha 1 u1 plus alpha 2 u2 plus dot 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 alpha n un. That is, u can be this vector u in u can be uniquely expressed as the linear combinations of the scalar and the vectors in the basis of u. U equal to alpha 1 u1 plus dot 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 alpha n un. Therefore, v equal to f of u now equal to f of alpha 1 u1 plus dot 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 alpha n un, and this can be written as alpha 1 f of u1 plus dot 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 alpha n f of un. Since f is linear transformation, that is, v can be expressed as the linear transformations of the element of the set S1. V belongs to the linear span of S1. Linear span of S1 is equal to V. That means any element in V, I'm getting it in the linear span of S1. That is, V is a subset of S1, and trivially linear span is a subset of V. Hence, L of S1 is equal to my V. That means S1 is a basis. Since S1 contains an element, therefore dimension of V is equal to n. Hence, dimension of U and dimension of V are equal, and it is equal to n. Hence, the theorem. Next, if V is a vector space of dimension n over the field F, then V is isomorphic to VNF. Let B equal to V1, V2, dot 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 Vn be a basis of V. If B belongs to B, then there exists unique scalar alpha 1, alpha 2, dot 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 alpha n, such that B is uniquely expressed as the linear combinations of the scalars and the vectors of B. That is, B is equal to alpha 1 B1 plus dot 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 alpha n Bn, where this alpha 1, alpha 2, dot 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 alpha n is a unique element in Bn. That is, Bn is a collection of n tuple. Its entry come from the field F. We define a function f from V to Vnf given by f of B is equal to f of alpha 1 B1 plus dot 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 alpha n Bn, which is equal to alpha 1 alpha 2 dot 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 alpha n. Now we shall show that f is my isomorphism. For that, first I will show f is my linear transformation. Next we will show f is 1, 1. Then we will show f is on 2. First, f is linear transformation. Consider two elements u and v in vector space V. Consider two elements u and v in V. Then u and v can be expressed as linear combinations of the element of the vector, element of the basis vector, that is alpha 1 b1 plus dot 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 alpha n bn, and b equal to beta 1 b1 plus dot 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 beta n bn. Now, for any scalars alpha beta in the field F, alpha x plus beta y is equal to alpha into alpha 1 b1 plus dot 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 alpha n bn plus beta into beta 1 b1 plus dot 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 beta n bn. In the next step, bring this alpha inside. This will become this one, and bring this beta inside. You will get this one. Then write the coefficient of b1, b2 dot 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 bn. I will get this alpha alpha 1 plus beta beta 1 b1, alpha alpha 2 plus beta beta 2 b2 plus dot 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 alpha alpha n plus beta beta n bn. Next, take the f image of this one and f image of this, that is f of alpha u plus beta v, f of right hand side. Using the definition of the mapping we have defined above, that is this one, we will get this one alpha alpha 1 plus beta beta 1, alpha alpha 2 plus beta beta 2 dot 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 alpha alpha n plus beta beta n. Then separate alpha and beta. I am writing, I will get this one alpha alpha 1 alpha alpha 2 up to alpha alpha n plus beta beta 1 beta beta 2 up to beta beta n. Take alpha common, this will be alpha into alpha 1 alpha 2 dot alpha n beta beta 1 beta 2 up to beta n. By using again the definition, this will be alpha f of u plus beta f of b. Therefore, f is my linear transformation. Next, we are going to show f is 1, 1. For that, we have considered f of u is equal to f of p. That is f of alpha 1 b1 plus dot alpha 2 b2 plus dot alpha n bn is equal to f of beta 1 b1 plus dot beta n bn. This implies alpha 1 alpha 2 up to alpha n is equal to beta 1 beta 2 up to beta n. Since this tuple is equal, so corresponding elements are equal, that is alpha 1 is equal to beta 1 up to alpha n is equal to beta n, therefore alpha 1 b1 plus dot alpha n bn is equal to beta 1 b1 plus dot beta n bn, that is u is equal to p. Hence f is my 1 1. Next we are going to show f is on 2. Let b belongs to bn, then b will be made in this form alpha 1 alpha 2 dot alpha n. There exists u belongs to p such that u is equal to linear combinations of this scalar with the vectors in the basis of p, that is u equal to alpha 1 u1 plus dot alpha n bn. And f of u is my f of this element, f of alpha 1 u1 plus alpha 2 to u2 plus dot alpha n un. And by definition of the mapping, we have defined above, that is this. This is my alpha 1 alpha 2 dot alpha n, and this is my b, that is f of u is equal to b. I am taking b in the codomain, I am getting an element in the domain such that b is equal to f of u. Therefore, f is on to, hence f is my isomorphism, that is b is isomorphic to bn f. Hence the theorem. These are your home assignment. Try to solve your home assignment. In case of any doubt, you should inform me. I will solve it for you. Remaining will be in the next lecture. With that, I would like to conclude. Thank you.